Hello everyone and welcome to Lecture 7 of our Probability Theory course. Today's topic is Random Variables and the Law of Distribution of a Discrete Random Variable. This lecture marks an important transition in our course. We're moving from random events to numerical quantities that describe random phenomena. Here's our plan for today. We'll begin by understanding what a random variable is and why we need it. Then we'll distinguish between discrete and continuous random variables with clear examples. After that, we'll introduce the law of distribution, also called the distribution series, and examine its properties. We'll also look at the distribution polygon as a graphical tool and then define the cumulative distribution function, fx, with its key properties. We'll work through a practical example involving defective items, and finally I'll give you a preview of mathematical expectation, which we'll cover in detail next time. So far in this course, we've been studying random events and their probabilities. For example, we could ask, what's the probability of getting heads on a coin toss? And we'd answer 0.5. But what if we want to describe a number associated with the outcome? For instance, how many heads appear in 10 tosses? Or how many defective items are there in a batch? Or what's the sum of numbers on 2 dice? In all these cases, we need a random variable, a way to quantify random outcomes numerically. This allows us to work with numbers instead of just events, which opens up a whole new world of mathematical tools. A random variable is a numerical quantity whose value depends on the outcome of a random experiment. Formally, it's a function x that maps the sample space omega to the set of real numbers. Let's look at an example. Suppose we toss a coin 3 times. The sample space contains 8 equally likely outcomes: H, 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 T, and so on. Now let x be the number of heads that appear. X can take values 0, 1, 2, or 3. Notice that x is not random itself, it's a deterministic function. The randomness comes from the experiment. For each outcome, x assigns a specific number. This is a crucial idea. A random variable is a function, not a random number. Random variables are divided into 2 main types. First, we have discrete random variables. These take a finite or countably infinite number of values that can be listed. Examples include the number of heads in 10 tosses, the number of defective items, or the sum of 2 dice. Second, we have continuous random variables. These can take any value within an interval, an uncountably infinite set of possibilities. You cannot list all possible values. Examples include a person's height, the time until a light bulb fails, or the temperature in a room. Today we will focus exclusively on discrete random variables. Now let's introduce the law of distribution. This is a rule that establishes a connection between the possible values of a random variable and their corresponding probabilities. For a discrete random variable, the law of distribution is presented as a distribution series, which is simply a table. In this table, the top row lists all possible values x sub I, and the bottom row lists their probabilities p sub I, where p sub I equals the probability that x equals x sub I. This table is also called the probability distribution of x. As you can see, it's a very straightforward representation. Each possible value has its own probability, and together, these probabilities give us a complete description of the random variable's behavior. For a distribution series to be valid, 2 conditions must be satisfied. First, the non-negativity condition. Every probability p sub I must be greater than or equal to 0. This makes sense because probabilities cannot be negative. Second, the normalization condition. The sum of all probabilities must equal exactly 1. This means that when we consider all possible outcomes, one of them must occur. These 2 properties ensure that we have a valid probability model. If either condition fails, the distribution is not valid. We can also represent a distribution series graphically using what's called a distribution polygon. To construct it, we plot points with coordinates x sub I on the horizontal axis and p sub I on the vertical axis. Then we connect adjacent points with straight line segments. This gives us a visual picture of the distribution, making it easy to see which values are most likely and how the probabilities are spread out. Let's look at a concrete example. Suppose we toss a fair coin twice and let x be the number of heads. The possible values are 0, 1, and 2. The probabilities are 1/4, 1/2, and 1/4 respectively. When we plot these points and connect them, we get a triangle shape with the highest point at x equals 1. This tells us visually that getting exactly one head in 2 tosses is the most likely outcome. The polygon clearly shows the shape of the distribution. Now we introduce another important concept, 8, the distribution function, also called the cumulative distribution function or CDF. It's denoted by f of x and is defined as the probability that x takes a value less than or equal to x. For a discrete random variable, we calculate f of x by summing all probabilities for values x sub I that are less than or equal to x. This function gives us the accumulated probability up to any point. For example, in our coin toss example with 2 tosses, f of -1 is 0 because there's no value less than -1. F of 0 is 1/4, f of 1 is 3/4, and f of 2 is 1. The key thing to remember is that for discrete variables, f of x is a step function. It jumps at each possible value. The distribution function f of x has 4 essential properties. First, boundedness. F of x is always between 0 and 1 inclusive for all real x. Second, monotonicity. F is non-decreasing, meaning that if x1 is less than x2, then f of x1 is less than or equal to f of x2. Third, limits. As x approaches -infinity, f of x approaches 0, and as x approaches positive infinity, f of x approaches 1. Fourth, right continuity. F is right continuous at every point. These properties must hold for any valid distribution function, and they are very useful when analyzing random variables. Let's work through a practical example. Suppose a factory produces items, and the probability that any given item is defective is 0.1. We randomly select 3 items, and we let x be the number of defective items in our sample. We want to find the distribution series for x. Since we have 3 independent trials, each with 2 outcomes, this is a Bernoulli scheme with n equals 3, p equals 0.1, and q equals 0.9. X can take values 0, 1, 2, or 3. Using the Bernoulli formula, we calculate each probability. The probability of 0 defectives is 0.1 to the power 0 times 0.9 cubed, which equals 0.729. For 1 defective, it's 3 times 0.1 times 0.81, giving 0.243. For 2 defectives, it's 3 times 0.01 times 0.9, which equals 0.027. And for 3 defectives, it's 0.001. Let's check the sum. 0.729 plus 0.243 plus 0.027 plus 0.001 equals exactly 1. So this is a valid distribution. Using the same defective items example, let's calculate the distribution function f of x. We have values 0, 1, 2, and 3 with probabilities 0.729, 0.243, 0.027, and 0.001. For x less than 0, f of x equals 0. For x between 0 and 1, f of x equals 0.729. For x between 1 and 2, it's 0.729 plus 0.243, which equals 0.972. For x between 2 and 3, it's 0.972 plus 0.027, which equals 0.999. And for x greater than or equal to 3, it's 0.999 plus 0.001, which equals 1. This staircase shape is characteristic of discrete random variables. Notice how the function jumps at each possible value. Finally, let me give you a brief preview of mathematical expectation, which we'll study in detail next lecture. The mathematical expectation, also called the mean or expected value, is denoted by E of x. For a discrete random variable, it's calculated as the sum of each value x sub I multiplied by its probability p sub I. This is the weighted average of all possible values, where the weights are the probabilities. In our defective items example, the expectation is 0 times 0.729 plus 1 times 0.243 plus 2 times 0.027 plus 3 times 0.001. This equals 0.3. The interpretation is that if we repeatedly sample 3 items from this factory, on average, we would expect 0.3 defective items per sample. This is also called the first moment of the distribution. Let's summarize what we've learned today. A random variable is a numerical function of the outcome of a random experiment. A discrete random variable takes finite or countably infinite values. The law of distribution is a table connecting values x sub I with their probabilities p sub I. For a valid distribution, probabilities must be non-negative and sum to 1. The distribution polygon provides a graphical representation. The distribution function f of x equals the probability that x is less than or equal to x, and it has 4 key properties: boundedness, monotonicity, limits, and right continuity. Finally, the mathematical expectation e of x gives the average value. The key takeaway is that the law of distribution gives us a complete description of a discrete random variable. That concludes our lecture on random variables and the law of distribution. Thank you for your attention. If you have any questions, please don't hesitate to ask. In our next lecture, we'll explore mathematical expectation and variance in much greater detail. See you then.